we'll begin with Jaro to tell us about monads.
Oh. There are monads involved, yes. So, yeah, I'll just start immediately. So this talk is about parsing data-dependent grammars with derivatives. And the goal of this work is to be able to write expressions like this. As you can see here, this is a parser that starts by parsing a number, and then it parses in a loop, and it parses a number of dot characters, which should be equal to the original number. Now, as Haskellers, you might think, why is this so difficult to do? Because parser combinators are monadic and can do this. But the problem with parser combinators is that you don't get nice things, such as being able to use left recursion and having good performance. That's another problem with parser combinators. So in this work, I'm trying to create an embedded DSL where you can actually, basically get the best of both worlds, get this data dependency and get all the nice theory things from context-free grammars that you used to. So this is an example where I use this data dependency. What is perhaps more interesting is to look at an example parser for expressions. So here in this parser, we can use this data that we pass from one iteration of the fixed point to another to indicate what the associativity and what the precedence should be of these operations. So I'm using the numbers 0 and 1 here to indicate whether or not you're allowed to use addition or multiplication in one of the branches. So that's what the data dependency allows us to do. And note that this is a left recursive grammar where we recurse into the parser P before we parse the operation symbol. So this, as I said, this allows you to combine the benefits of context-free grammars and the monadic style of programming. This is an empty slide. Oh, no, it's an animated slide. So to attack this problem, I tried to find the simplest way to do parsers. And the simplest way I've come up with is, or I've seen online, is parsing with derivatives. So let's say we know that the meaning of a certain context-free grammar is a set of strings. Then the derivative is taking a context-free grammar and a character to produce a new context-free grammar, where then the meaning of this new context-free grammar is all the elements of the original context-free grammar, but then only those which started with that character. So we essentially filter out all the strings that start with that character and then also remove that character. So we're left with this B and CD in the derivative. And finally, we need a function called nullable, which determines whether the empty string is in the meaning of the grammar. And with this, you can iteratively apply derivatives to parse a whole string. And at the end, you need to call nullable to see whether it actually has parsed anything. So this is based on a blog post from Well Typed. Let's see. Yeah. But I've extended it a bit, so in the blog post by Well Typed, they only look at recognizing languages. I've extended it a bit to actually produce results. And I'm using this data type for that. I don't think I can go very much in detail, but I want to switch quickly to an implementation I've written. So here is the same. Is it still visible? No. That's bad. Okay, I'll just do this. And we want to zoom in a bit. I want to close this. So here I have an n-dots parser, which is the first example I showed, where you we parse a digit, not a full number in this case, but that doesn't matter, and then a number of this dot character. So yeah, and that is able to parse. And similarly, this expression parser works, and it successfully filters out the applies associativity rules in this case, so that the addition is right associative. One problem with this approach is that this version that I'm showing right now will take exponential time in the length of the string, so even parsing things with only 10 characters will take a long time. And to combat that problem, I've written a lot more code to get a actual deep representation of the grammar, so that I can actually refer to everything by variables, and I can inspect the whole structure of the context-free grammar. And that also means I can nicely show what it's actually doing. So let me quickly show that if there's still time. So on the right here, you can see in the terminal window that it produces a bunch of we can show the steps that it takes while parsing. If I can find my cursor, I can move. And I've actually hacked this together to produce some Haskell-like syntax. So I'm using an online pretty printer for Haskell syntax. So here's the exact same thing that it produces. Let me zoom in a bit. Is this readable, hopefully? So here's an example of the expression parser. And this expression parser, I've not quite been able to get it to perform in linear time. And the way you can see that is we see the first step here at the top, and we see a second step where we now have 2 fixed points, and we have a third step where we still have 2. That seems hopeful, but then the fourth step has 3 again. So it will, the grammar will grow linearly while we're doing the parser, which means we also need to traverse the whole grammar again and again for each new character. Yeah, but the way I'm hoping to tackle this is to write more analysis on this data structure, because as you can see at the end, there is, you can see that there is some redundant, some of these fixed points are redundant, and it should be possible to collapse them into one and keep the whole grammar representation constant size. And that would also mean that we have linear time parsing. Okay, thank you.
I mean, do you want to just project from there?
Yes, yes. It works. Does this work?
I've never tried it either.
Is there anything at the screen?
We're about to find out. How does that?
Yes, yes.
Okay.
Oh, what do I do?
Can you?
Is this better? Oh, okay. All right. Yes.
I don't know if we should call these technical difficulties or technical triumphs, but the next lightning talk
Okay.
is on random
Thank you. So, how does the world's finest imperative language compare with the world's most prototypical imperative language, which is C? So in C, if you wanted to take a character from standard input and output it, this is how you will write it in the first line. Put char, parens, get char, parens, close parens. The equivalent in Haskell, the isomorphic equivalent in Haskell, is put char, get char. But as you know, that does not type check. The idiomatic way to write it in Haskell, using the monadic combinator that also happens to be Haskell's logo, is you have to flip the two sub-expressions, and you have to say get char, monadic bind, put char. Now, you could use the flipped monadic bind and write it, again, to make it more like C, using put char, extend. The flipped Haskell, the Haskell logo that's flipped left and right is called extend. And actually, Ed, I have stickers of extend, and if you show up in Singapore, I will take your sticker if you take mine. So this is quite likely GHC proposal number 23 or something, but in other words, this is already quite old. The point is we really want to overload white space and get rid of those monadic combinators and be able to write put char, get char, right? That is, I don't know how that is going on. But imagine then in a world where all our functions are auto-fmapped and auto-lifted, right? And auto-monadic bound. And so put char really has kind of this type signature of IO char. So now we have a problem. It seems very artificial, I know. I'll come back to that. Now you have to write put char return A, and it's like, well, the return shouldn't be there. We really should get rid of return, because we really want to write put char A. So this is the narration that I have. It's like, well, we already have that. You don't have to get rid of return. Return is an injection and an embedding that is really very unnecessary. And if you don't like this narration, consider the fact that there are a lot of beginner Haskellers who are trying to get the hang of using these monadic combinators, and who are stuck prematurely using return. It's like, oh, how do I get out of return? The point is that you never use return, as we all know in Haskell, until you actually have to embed that pure value into the monadic space. So if if pure values were a subtype of monadic values, then you wouldn't need return at all. And so what I'm working on is basically trying to see if Haskell's type system, which is really parametric polymorphism plus the type classes, whether we can bring the work on the more recent work on algebraic subtyping into it. Subtyping, as you know, brings lots of benefits. In particular, we can fix the numeric type class, right, and get the subtypes that I think we deserve. So, subtyping.
Does anyone else have any questions?
Rather than want to go further to the center. So my biggest concern is when you wrote that put char, IO char to IO unit,
Yeah.
when does the effect happen? How do I drive when that char gets read, right? Like I have lost control
Yes.
over
Yes.
my effects. And that means that there's a number of programs that I can either no longer say or I have to come up with some new vocabulary to say, which is
Yeah.
going to sound an awful
Yes.
lot like being able to say return.
Yes, yes. So for those special cases where you really need to order the effects, like for instance, then there's, I don't think we're gonna completely remove it, but the point is that if you have a pure function and you are quite happy with the order of the effects, taking place in the order of the parameters, then it happens automatically, right? I think what you're talking about is you're saying something about what happens. There's a distinction between lift M2 of a function and swap lift M2 of a function. Something like that.
Or bracket.
Yeah, lift M2 dot flip, right? Applied to that function, right? Or bracket. Yes, exactly. So yes, there will be an escape hatch, but I submit to you that most of the code you just follow the effects with the order of parameters. Yes.
It's been a while that I looked at this, but for reference, I think Idris does try to solve this problem with a bang operator, where you can write your puts_line line, bang gets_line line, and you can nest this arbitrarily deep with parentheses, and I forget the details, but there is some definition for in which order, exclamation point.
Yeah, the bang is on the value or on the equal.
So you would write puts_, bang gets.
Yes, the idea of, unwrapping that.
So it's purely
Yeah.
syntactic. It
I know.
still uses the same kind of monadic principles. But yeah.
I know. You see, what I like to also get rid of is do notation. In other words, there are cases where you have some pure code and you insert some effect in it, and it's like, oh no, I've got to redo everything and rewrite everything in do notation, and it turns out that you don't need it after all, and then you rewrite it back to let. So there's only one binding, and the compiler can infer whether or not it's effectful or not. It's a bit like what you do with implicit parameters, right? But so one binding.
Okay, so maybe this is just a troll question, but
Go ahead.
when I think about num, right? I mean, you mentioned, right? So negate the type parameter, a appears both positively and negatively. So is the num type class contravariant or covariant?
The num type class,
If A is a subtype of B, does num A imply num B? Does num B imply num A? Which would you like?
See, that's the thing is like I don't think in terms of the num types. It's like I want naturals to be a subtype of integers and integers to be a subtype of reals and reals to be a subtype of complex numbers. So the num type class. I mean, like the contravariant actually comes in only when we talk about a function and an explicit function. So for instance, plus, right? Well, if you have two naturals being added together, that will produce a natural which you can feed into anything that's expecting an int or a real or a complex number.
You run into the same issue with monoid, though, not just, you don't need to go all the way to
All the
num,
way.
where the fact that most languages have a numerical hierarchy like that conflates the issue. The Cohen contravariance of the fact that monoid from append has A occurring in both positive and negative position also runs into this issue. Like if you have an effectful M, you have a problem with, well, the monoid laws make me want to make a commute, but my underlying effects may not.
Yes, I mean, yeah. Are we treating the monoid as merely, I mean, the thing is that what I'm proposing, is not something where you have a kind of like an ACDA proof system built into it. Some people just use monoid, as kind of like a semi-group with some pointed element. And how are we going to prove that it actually is monoidal, right?
I mean, yes, you can't write the laws down in Haskell, but the thing is people reason with them.
Yeah, but if you want to go into that, I think the one start is subtyping.
So if I understood what you were proposing correctly, was that not only do you want A to be a subtype of M of A, where M is a monad,
Yes.
but also if you write put char of get char,
Yes.
you want a bind to be automatically inserted, you might say.
Yes,
Lifting the
a
get char out.
compiler, a type system that truly understands monads and not just, like what we have today, where we have type classes, and type classes is strong enough and good enough to encode bind and return.
So if you have then, if you have a function whose argument type is M of A, then that function is intended to be passed a computation that might be performed several times or not at all, or in different places. So you need to have lazy evaluation of effects, as it were, at that point. Whereas if you have an argument, a function of type into something and you pass it a monadic value, then you want the effect to happen first. So that's going to give you a strict semantics. Now, what I wonder is what happens if your function is polymorphic? So you can't tell when you're compiling the source code whether it should be interpreted in a strict or a lazy manner. No doubt it's possible to
Yes.
figure that out, but it seems difficult.
If you could have a concrete example, I would love to, because I think there is some there is a common misconception. It's like strict is actually a subtype, and so lazy is actually monadic over strict. So yeah.
Okay, so I think any function with an argument of type f of a for some type f, where that might be a monad or it might not be.
Yes.
Like map, for example.
There we go.
For example.
Maybe we should
Yep.
All right, our final lightning talk will be delivered by Ed Komet.
All right, hi there. So a while back, I started playing around with linear Haskell for a bunch of things. And one of the problems that I have when working with linear Haskell is we can do a lot of things with linear Haskell, but not everything. So I want to look back at like some bits about linear logic very briefly, which is sort of, and constructive logic in general. So Brouwer, back when he was working on linear logic, or on constructive logic in particular, spent a lot of time thinking about like, gosh, a function from A to B is actually a thing that, is a thing that transforms a proof of A into a proof of B, right? But something is sort of lost in that equation, which is that you lose the contrapositive version of that statement. You kind of get it back in like a Hating style setting where you've got like not A is that A implies void, and therefore you can compose those two things together, but it's not quite full strength. You can't not A is A, right? We don't just have the ability to sneak into any continuation passing style thing and pull it out. So there's another trick that I like. I'm going to derive a logic due to Valeria de Paiva and Martin Hyland, I think, called full intuitionistic linear logic. This is a constructive logic which has not A is A. And it's built in this particular case by using something called a chew space. So what I do is this. I say in chew, Hask over void, we say that objects are pairs of objects equipped with an arrow to void, such that if you had a proof of A and a disproof of A at the same time, I can blow up your universe, right? The reason why I'm using void here, de Paiva used like a two object thing, where they could have like a true and a false statement, is because you would have to prove this little diagram commutes when you make an arrow. So an arrow between this pair and this pair is an arrow going forward on A's and an arrow going backwards on the second half of it, which is basically providing the contrapositive statement. Such that this diagram commutes. Well, I can't prove things commute, which is just the subject of, of conversation just now, except for the fact that arrows to void are all trivial and uniquely determined. So I can prove that. So now we can go into Haskell. Now, working with pairs of types is not a particularly natural construction in Haskell, but what I can do is I can say, hey, I want not to be a type family such that it's injective, and not A is A, and that's how we say that here. And proposition is one such that I have A and not A entails R, anything you want. So that's void, just unpacked for all R. And then I could use undecidable superclasses. Thank you, Simon, for giving me that at some point. But it makes the compilation so slow and the error message is so inscrutable, I don't. And so it's just easier for me to build the half of the proposition and then tuple it up with itself. Now, with this, I can actually build proper linear logic. Now, Mike Schulman actually has a paper on this. His version of it can only prove an affine logic because he only builds it over a Hating algebra. But I'm building it over Haskell, and Haskell has this lovely linear Haskell thing where we have linear arrows. And so what I have is kind of crappy linear arrows that don't have attached to them the contrapositive statement, but I can build the right thing out of the wrong thing. And so I can wind up with propositions for bottom and all sorts of, top, and there's 4 different units involved here. The first interesting connective is to start talking about what a width is. So like what folks have some intuition for sums and for tensors in linear logic, which is that a tensor is that you have an A and a B and you have to use them both, gosh darn it. And an either is an A or a B, your choice. But there's also the concept of, hey, you've got a tensor-like thing, but you only have the first and the second projections on it. You have an A or a B, your choice. And those are the 3 connectives that people wind up with intuition for. But you can go a step further and actually build par, except for the fact that like the sort of vending machine metaphor that people have in their heads don't work for it. Because it's the only connective in linear logic that really requires you to have refutations on hand. And so par winds up being the connective that says, hey, if you gave, it's like, I'm going to refute a pair. I'm not going to refute it by giving you, I'm not going to say, what you say A and B is true, and I say, no, it's not. I'm not going to tell you which one's wrong. I'm going to wait until you tell me one of them's right, and I'm going to hit you upside the head with the other one being wrong. So I don't make the choice. I have to delay the motivation of that choice. That's what par is. And we can turn around and build lollipops out of par. So we built par out of the crappy arrow that we have in Haskell. And we can build lollipops off of that. And the problem is if I build them, they'll be harder to use. So I can make a type class that actually takes my Haskell arrows, shows that the refutations for Haskell arrows are isomorphic to the ones in lollipop. And I'll get to my joke here, or the punchline, and then I'll yield the stage. Which is that what we can do is we can start saying, well, I want to do enriched category theory or something over this. So I'm going to work in and say, hey, look, a linear arrow for category. But the problem is this used the Haskell arrow. So we can turn this around using my lollipops such that if you disproved that there is an arrow from A to C, you get all the baggage about one of these 2 things not existing. Which is exactly what you want. I don't know which one doesn't exist, but when you tell me one of them exists, I will punch you in the face and tell you the other one doesn't. And we can take this down to reasoning about all of the properties about, like, let's say, like how would I swap a tensor or a either or a with or a whatever. Now, if I write these things out directly, I get the Haskell arrows. But I can use those to bootstrap my lollipops. Once I bootstrap my lollipops, I can bootstrap isomorphisms. Now, the swap for par is one name that you can use as if it was a Haskell arrow. You can use it as if it was, because the lol iso is instantiated for the normal Haskell arrow, because you can construct it using the information from an isomorphism, and disproving it disproves the isomorphism, which is what I need in order to make these things compositional. But I have to wind up building a plugin in order to actually reason my way through, and the rest of it becomes crazy, and I'm going to stop now because I'm way over time. But the things that I wanted to show was that you could actually build full intuitionistic linear logic, a place where not A is A. It's not the Hating negation. It can be built on Haskell, and it can actually be made usable. And the proofs are terrifying, but they encode as things like this. This is how BIMAP works for par. All right, thank you. All right. I'm assuming I'm out of time for questions, so I will run.